Hello, dear students. It is the fourth lecture, first of the fourth lecture, which is a major on summarines, and the course is MMTC 202. So, in this lecture, we discuss a measure on a submarine, which can be thought of as a generalization of length and area. So, let's first define a measure on a submarine. In order to define this measure, we first define a set function. What do we mean by a set function? Definition of a set function. Let S be a class of sets, then any function, say f from S to R is called a set function, is called a set function. So in a set function, we calculate the value of a function on a whole set, not at a point. Next, we define a measure. It's also a set function actually. But in this measure, this S summaring, let S be a summaring on a set X, then a set function mu, which we denote by mu, from S to 0 to infinity, including infinity, is said to be a measure, a measure on S if it satisfies the following properties. Property 1 is its value on this free set is equal to 0. That's property 1 of measure. And second property is that it's sigma additive. Sigma additive means that if an is any disjoint sequence in S. If n is any disjoint sequence in S, if an is any disjoint sequence in S such that union n runs from 1 to infinity a and belongs to S, then this mu of that disjoint union, mu of union a, should be equal to summation n runs from 1 to infinity mu of a. And this property is called a sigma additive property. So a measure is a set function satisfying these two properties. Its value on phi set is equal to 0, and if we have any disjoint sequence in S, in that summaring, with the property that the union of that disjoint sequence is in S, that's a requirement because we have to calculate mu of that disjoint union. So we can only calculate this value if this union belongs to the domain of mu. Here the domain of mu is S, so that means this union should be in S. So A is a disjoint sequence in S. With the condition that the union belongs to S, then it should satisfy this property. Mu of disjoint union n runs from 1 to infinity an is equal to n runs from 1 to infinity mu of an. And this property is called the sigma additive property. And the function, this mu set function, it's called a measure on S. So that's the definition of a measure. So now if we say a triplet X as mu a major space, we call this triplet a major space. When we call it major space, if S is a semiring, if S is a semiring on X and mu is a major on S. So next, in future, whenever we say that triplet is a major, it means that S is a semiring on X and mu is a major on S. So next we have a theorem. Let X as mu be a major space, major space. Major space means that S is a semiring on X and mu is a major on X. Then following hold. First property: if A1, A2 up to AN are disjoint sets in S such that the union of these members, there are finitely many A1, A2 up to AN, it also belongs to S, then mu of that finite disjoint union, it's equal to summation mu of A k runs from 1 to n. So that's the first property of major space. If we have this, if A1, A2 up to AN are finite or disjoint sets in S, then such that this union belongs to S, and then mu of the finite union is equal to sum of mu of A k runs from 1 to n. And we call this property finite additive property. This is called finite additive property. Finite additive property. Finite additive property, because here we have a finite class of sets k runs from 1 to n. It's called a finite additive property. And second property is that if A comma B belongs to S such that A subset of B, then mu of A is less or equal to mu of B. So that is mu is monotone. So if excess mu is a major space, then this mu is finite additive and it is also monotone. That's this theorem. So first we prove that mu is finite additive. Mu is finite additive. proof of the theorem. So finite additive means given any finite class of sets which are also disjoint such that their union is in S, then mu of that finite union is equal to sum of mu of a case k runs from 1 to n. So let's take a finite number of sets. Let a1, a2, so on an be disjoint sets in S such that union AK k runs from 1 to n belongs to S. Now we can replace this finite union by countable union. Now we can write this union k runs from 1 to n. AK is equal to union k runs from 1 to infinity mu of AK, mu of AK, where this a n plus 1 is equal to a n plus 2, so on. They are all phi sets. They are all phi sets. So these two unions are same. And both they are the members of S, and mu is a set function. It means that their mu values must be same because mu is a function. So union k runs from 1 to n, AK is same as mu of union k runs from 1 to infinity, AK. But since mu is sigma additive, it's a major on S, and they are disjoint A1, A2 up to a this infinite class. It's a disjoint class in S. They are the disjoint members in S, and therefore this is equal to summation k runs from 1 to infinity mu of AK. But mu of AK plus 1, AK plus an plus 1, an plus 2, they are all phi's, and mu of phi, they are equal to 0. They are all equal to 0. So therefore this summation is same as summation k runs from 1 to n mu of AK, because mu of an plus 1, mu of an plus 2, and so on, they are all equal to 0. So that means mu of this finite union is equal to summation k runs from 1 to n mu of AK. That proves the first part. Now we prove second part of the theorem, that is this mu is monotone. Second part, mu is monotone. Every measure is monotone. So for this we take any two sets in the domain of mu, that's semiring. Let A comma B belongs to S such that A is subset of B. We show that mu of A is less or equal to mu of B. Okay. Okay. Since A is subset of B, now we have B which is equal to A union B. A is subset of B. This is B. This is A union B is whole B, and this B is equal to A union. It's equal to A union B minus A. That portion. So B is equal to A union B minus A. It's a disjoint union. B is equal to A union B minus A. They are disjoint sets. Now A and B, they are the members of S, and S is a semiring, and we know that difference of any two members of a semiring can be written as finite disjoint union of members of S. So it can be written as A union, this B minus A can be written as C1 union C2, so on union Cn, where these Ci's, they are the members of S, and Ci intersection Cj is equal to phi. Okay, this since A and B minus they are also disjoint. Therefore, A is disjoint from each Ci. It is disjoint from C1. It is disjoint from C2. It is disjoint from Cn. So that means this class A, C1, C2, Cn, it is a disjoint class of sets in S. So if I want to find the mu of that disjoint union, finite disjoint union, it is equal to sum of the mu's by part 1. Because mu is finite additive. So now we find mu of B. So therefore mu of B, it's same as mu of this union, mu of A union C1 union Cn. So look at this union. It's a disjoint union, finite disjoint union of S, and this union is equal to B. It belongs to S. So we can write it as mu of A plus mu of C1 by part 1 of this theorem plus mu of Cn. So this mu of each set is greater or equal to 0. Mu is a function from S to 0 to infinity. So mu of each set is greater or equal to 0. Therefore this is less. This is greater or equal to mu of B. So that means mu of A is less or equal to mu of B. So that proves this mu is monotone. That's the first theorem on this measure. Next, we give some examples of measure space. So, the first example, it's called a counting measure. Counting measure. Counting means we have the mu of the set is equal to the number of the elements in set, cardinality of the set. Counting measure. So let x be not equal to phi and s is equal to powers of x. Then we know that S is a semiring. Then we know that S is a semiring. Now we define a set function on S, and then we show that that set function is a measure. Define a set function mu from S to 0 to infinity by mu of A is equal to cardinality of A if A is finite. If A is, suppose the cardinality of A is 10, then we define mu of A is equal to 10. And it's equal to infinity if A is infinite set. We show that this mu is a measure. That means we show that mu of phi is 0 and mu is sigma additive. Those two properties of measure. We show that mu is a measure on S. The first one, it's trivial. Mu of phi, since phi it's a finite set, so it's equal to the cardinality of phi, that's equal to 0. So mu of phi is 0. First property is trivial. So now we prove its second property, that's sigma additive. Now we prove it's sigma additive. Second property, that mu is sigma additive. So for this we take any disjoint, so we can say let A and be a disjoint sequence as such that union A in errors of 1 to infinity belongs to S. This is always true here. Union is always in S because S is the class of all subsets of X. So we don't need to write it here. So we need to show that we show that mu of union an runs from 1 to infinity is equal to summation n runs from 1 to infinity mu of A. That's what we have to prove. So we consider certain cases here. It's case number 1. In case union A and n runs from 1 to infinity is an infinite set, then mu of union n runs from 1 to infinity an is infinity by definition of mu, because mu of infinite set is equal to infinity. We show that this sum is also infinity, so that proves the equality. Mu of union is equal to sum of mu of ans. We prove that we prove that summation n runs from 1 to infinity mu of an is infinity. So in case there is a set, there is some set an which is infinite, then this sum is infinity. So in case there exists some ai such that ai is infinite, then this sum is infinity because mu of ai is infinite. Set is infinite. And runs from 1 to infinity, mu of an is equal to infinity. So if one of the sets is infinite, then this sum is infinite. But in case each set is finite, in case each a n is finite, in case each n is finite. Since the union is infinite, so therefore there are infinitely many sets AIs which are non-empty. Since union A and n runs from 1 to infinity, so there exist infinitely many i's such that AI is infinite set. For infinitely many AI's, so this AI is non-empty. AI is non-empty. So suppose A1 is non-empty, then mu of A1 is equal to the number of elements in A1, because n is finite, each n is finite. Say let's take A1. A1 is finite and it's non-empty, then it must contain certain number of elements. So in that case, mu of A1 is equal to number of elements. So similarly, suppose if A3 is non-empty and it's finite also but non-empty, then it has a certain number of elements, finite number of elements, then in that case mu of A3 is equal to number of elements of that set. But there are infinitely many such sets because the union is infinite. So therefore summation mu of n runs from 1 to infinity must be equal to infinity. Because there are infinitely many AIs such that AI is non-empty. So the measure of those sets must be greater or equal to 1. This one repeats at least this one repeats infinitely many times in the sum, so it will be infinite. It will be infinite. So therefore, in this case, mu of union, which is equal to infinity, and sum of mu of an is also infinities. So that proves this sigma additive property in this case, that if the union is an infinite set. Now we assume that if union is finite. Now if union an runs from 1 to infinity is finite set, then mu of union is equal to number of elements in this set here. And there are also disjoint sets here, and it's also finite. So then there are only finitely many, then each n is finite. That's trivial. Then each an is finite, and there exist only finitely many ai's which are non-empty. Also there exist finitely many ai's which are non-empty, because if there are infinitely many ai's which are non-empty, then union must be infinite set. So there are infinitely many ai's. Say, let's write those finite number of sets which are non-empty. Say ai1, ai2, so on up to aik, suppose. So therefore union n runs from 1 to infinity an is same as union I runs from 1 to k. Say, let's write here, m runs from 1 to k a I m, because the remaining sets are the empty sets. So it means that mu of union n runs from 1 to infinity a n is same as the mu of union a I m. M runs from 1 to k. It's union here. It's here. It's union. It's equal to mu of union m runs from 1 to k a I m. And that set's a finite set. It's equal to the cardinality of the set. M runs from 1 to m. So it's m runs from 1 to k a I m. Number of elements in this union, finite union. And we know that number of elements in the, say, A union B is equal to number of elements in A plus number of elements in B if the sets are disjoint. And here the sets are disjoint, therefore it's equal to number of elements in A1 plus number of elements in AI2 plus number of elements in AIM. Since the remaining sets are null sets, the cardinality of those sets will be equal to 0. It's equal to number of elements in A1 plus number of elements in A2, all the sets. So this sum also contains these sets as well. But now there are certain sets which are null sets, and the cardinality of those sets will be equal to 0. It's equal to summation mu of an runs from 1 to infinity. So that proves this property, sigma additive property of mu. So thus mu is a measure. Thus mu is a measureness. Thus mu is a measureness. So now we have one more example of a measure. So therefore excess mu is a measure. Excess mu is a measure space. So next one is the counting measure. Next one is the counting measure. Not the counting measure, that's the Dirac measure. This was the counting measure. Next one is Dirac measure. So Dirac measure now. Next example is the example which is called Dirac measure. Dirac measure. That's Dirac measure. Dirac measure. So what's Dirac measure? Let x be not equal to 5 and s be equal to power set of x. Then we know that s is a semiring. Then s is a semiring. Then s is semiring. It's already done in previous lectures. It's a semiring. And now we define a set function. We define a set function mu. Okay, it's not like that. It's a Dirac measure. It depends upon a point. Now for each fixed a belongs to x, define a set function. That's why it's called a Dirac function. Actually, it depends upon some particular point. Define a set function mu from s to 0 to infinity by mu of a is equal to 1 if a is in A. Mu of a is 1 if a belongs to A, and it's equal to 0 if a is not in A. So actually its value is evaluated at a point actually here. In fact it's a set, but it depends upon this point A belongs, whether A belongs to A or A is not in E. It depends upon that. So whenever it is in A, we take its value equal to 1. Whenever it is not in A, we take its value equal to 0. So we show that this mu is a measure. We